Perfect. Okay. Uh, last time we were talking about branch prediction. So the plan for today is that I'm going to finish the remaining slides for that. And then we're going to do a little bit of review and talk about the quiz one and all that. Okay. So if you remember, we talked about branch prediction and doing taken branch kind of approach. And for doing the taken approach, what we need to do is knowing the outcome of the branch during the fetch state. Why? Because essentially when we have an instruction like, add instruction and branch equal instruction and then an XOR instruction, fetch goes, add goes to the fetch, and then add goes to the branch, to the decode. Then branch equal comes, and then it goes to the fetch, right? And now remember, I want to be able to predict taken, which means that I want to basically go to wherever place that this branch equal is going. So at this point, I need to know that this is a branch, and I also need to know the address, the target of this, okay? In order to do that, we use the BTB, right? So the BTB was this structure that basically you kind of like feed the PC as the index. It gives you the target address. And then you can basically take that target address, if this is indeed a branch instruction, and your next instruction, the next cycle would be that target address, okay? And then we talked about kind of details of the BTB, who updates the BTB, how do we guarantee that the BTB always works, and we essentially said that the way that we're going to update the BTB is that whenever we know that this is indeed a branch instruction in the decode stage, and we know the actual target address of that branch, then that's where we're going to update the BTB. As a result, we always guarantee that the things that are inside the BTB are the correct branch addresses, okay? So that was kind of like the main thing. And this was kind of the recap that we had, that, okay, we want to reduce two things: the miss penalty and the accuracy or miss rate, okay? In order to reduce the miss penalty, what we did was, originally we had the branch prediction resolve at the memory stage. We bring that back into the decode stage, but that has high miss rate because we are always predicting not taken. In order to be able to predict taken, we also introduced the notion of BTB, okay? So that was kind of where we are at. And then we kind of said, okay, this generally would be kind of like, format like this. For non-branches, nothing happens because there's nothing in the BTB. We just continue normally. Then there is two group of branches: the branches that have seen before and the branches that have not seen before. For the branches that have not seen before, in other words, they are not already in the BTB, then again, nothing happens. You predict not taken and you continue. But then there are branches that you have seen before, and those that are branches that you predict taken. It may not be correct all the time, so it still could be misprediction. And we already know how to deal with misprediction. The logic for misprediction was like flushing and all that. So same story still applies here. You do the misprediction when necessary. You do flushing when necessary, but this gives you a little bit more accuracy, okay? And we also talked about why this is actually works. The reason for this is locality, the principle of locality. Particularly temporal locality is the one that is very helpful in this case, because essentially what we are saying is that if we see a branch, it's highly likely that we're going to see that some branch in some near future. The reason for that was the fact that most of the part of the time in any given program is in some form of a looping behavior, in some of repetitive behavior. As a result, there are going to be some repetitive branches. Okay? This was the structure of the branch. We kind of talked about kind of the marker architecture. We eventually kind of like show you this design here. Okay? We said that essentially the way that we're going to do is that this is what we call a tag BTB. So we take the lower bits of the PC to index into the table. We said that we ignore the first 2 bits. The reason for it is that the first 2 bits are considered always 0, 0 because we always go to a multiple of 4 for PC. So there is no need to actually deal with that 2 first bits, always 0. So we start with bit number 2 and go up. The size of the index depends on how many rows I have in my BTB. Typically, BTB, you can think about it as a structure with like 256 kilobytes, 512 kilobytes size in this range. So usually you have like 64, 128, that type of entries in your BTB. Your BTB is not going to be massive, okay? So as a result, you need to like 7 bits, 8 bits, 9 bits, 10 bits, depending on the size of the BTB to address, okay? And then what you have in the BTB is 2 things. You have what we call a tag, and we have what we call the address. This should be address to make things a little bit more easy for people. So this is your target address. The target address is basically the next PC. It's the value that PC should take for the next instruction. So it's a full 32 bits, okay? The tag can also be full 32 bits, right? Because you want to basically compare this entire thing with this entire thing. So it could be 32 bits. But also, if you store all the 32 bits, you are storing some redundant information. So you can further optimize this table if you want to. For example, there is no need to store these 2 bits, right? These 2 bits is always 0. So you can only store the 30 bits instead of 32 bits. Another thing that you don't need to store is this index. Why? Because essentially index is used to index the table. So you already know which index this is, right? So you don't need to store that as well. So what you can store is basically 32 minus index minus 2. So that would be the size of the tag. This part is still 32 bits, but this part could be less than 32 bits. So you kind of save some space. This is just an optimization, okay? In addition to that, what you do is you have a comparator, which basically what it does is that it compares the tag with this tag that you have stored. If this is a match, it means that I have seen this branch before. It's not guaranteed that it's always going to be a match, but if I've seen this branch and I have stored this branch in the BTB, that would be a match. If it's a match, then this will be equal to 1, which means that in this multiplexer, instead of choosing PC plus 4, I'm choosing whatever address that is stored in the BTB. Okay, so that would be basically the logic that we are following. And this would be my next PC. So this is your next PC. As you can see, for majority of instructions, nothing will be inside the BTB, so the match will not be satisfied. There will be a miss in BTB. As a result, you pick PC plus 4 and you continue. But in some cases, there will be a match, so you predict taken and you continue. Got a question? Yeah. So let's see what is. So the question is like, what is the difference between index and tag? Let's see what we want to do is that this is your PC, right? So you have this PC and you want to compare it with the stored PC that you have inside this part, right? So you want to compare these two. You want to see, is this the same branch that I've seen before or not? How do you do that? You store the PC of that instruction, you compare these two together, okay? So the eventual goal is comparing the current PC with the stored PC, okay? So option number 1 is that I store the entire PC, do 32 comparison, call it a day, move on. What I'm saying here is that there is opportunity for storing less number of bits. You can always creates the 32-bit by doing this. How? Essentially, the way that you're going to do this is the following, that you're using, so first of all, the first 2 bits always 0, 0. There's no need to store that. You can always concatenate 2 zeros at the end of whatever you're storing here, okay? Number one. Number two is that this is row by row, right? So think about, for example, this is 3 bits, so some number between 0 and 7, okay? So the way that I store this is that the value here would be for row 0, the value here would be for row 1, and so on and so forth. So this is 0, 0, 0, this is 1, 0, 0, this would be 0, 1, 0, and so on and so forth, okay? So how do I recompute my PC is that I take this value, okay, whatever this tag is, I concatenate this index, and I concatenate 2 zeros, and that would be 32 bits. Okay? So that's what I would store here. So the bigger the index is, the less bits I need to store in my tag. I just concatenate things together, and I have my table. I'm just trying to store less bits. That's all. Logic-wise, nothing is different. You, at the end of the day, you compare 2 PCs together. Okay? Yeah. So you can, I think my terminology maybe here is a little bit confusing. So in the entire thing you can, so usually we call this a tag table and we call this a BTB. The entire structure could be also referred as BTB if you want to. But generally this part is where you store your PCs, and this is usually what refer as to the this is the BTB part of it. But yeah, so BTB in general, this is structure needs a tag store and needs a data store. The data store is where you store the 32 PC target address. The tag is whatever tag that you decide to store. You can decide the entire PC there too, or you can just have some sort of a smaller version of it. Okay? So this would be how your fetch state look like. So you kind of like in parallel with the instruction memory, you also look up in your BTB, and then this will decide your next PC basically. Okay? All right. So the last thing I want to talk about for branch prediction so that we move on from this topic is that so far we've learned 2 strategies, that we either predict not taken all the time or predict taken all the time. But in reality, there is dynamic behavior. Not all the branches are taken, not all the branches are not taken. So if I really, really want to push this further and really increase the accuracy of my quote unquote branch predictor, what I need to do is some form of a dynamic behavior. More than that, there's actually different branches, different types of control flow instructions, and each one kind of behave differently. So what you will see later is not only I have one type of branch predictor, usually modern processors have bank of different branch predictors, each of which is useful for one thing. So let's actually see what's going on here. So if you think about your control flow instruction, your JAL, JALR, BEQ, B not equal, and so on and so forth, there's actually five different groups that you can think about. There are conditional branches, okay? Conditional branches are those that are checking some conditions. Branch equal is an example, right? The direction of that branch during the fetch state is not known. That is, we don't know whether this branch is going to be taken or not taken. Whether or not it's going to be taken depends on the condition itself. So for example, if you have an instruction like branch equal x1, x2, some offset, whether or not this branch is equal depends on the value of x1 and value of x2, and we don't know that during the fetch state. We know that for sure, okay? What are the possible next fetch addresses for a conditional branch? There are 2 possibilities. Either the branch is not taken, as a result you do PC plus 4, or the branch is taken, that you do PC plus offset. So these are the 2 possible directions for this branch, right? And then when do we know actually when the branch is resolved? With the current design, we know it at the decode stage. right? So we have the condition for checking the branches and all that, okay? Then we have unconditional branches. This is your JAL and JAL-OR. The difference between conditional and unconditional is that for JAL and JAL-OR, you know that your branch is always taken. As a result, you also know always that what is the possible address. The address is always the RS1 plus the offset if it's a JAL-OR, or if it's a JAL would be PC plus offset, right? And then again, when we know exactly what is the address, we know it during the decode stage. Then we have these pseudo instructions, which if you remember, these pseudo instructions are translated into JAL, JAL, or branch instructions. But the reason that I'm showing it this way is they're slightly behaving slightly different than regular branches. So call is always taken. So it's like similar to JAL or JAL. The address is also the same, and the decode address is the same. So the call and conditional is somewhat similar, but return is always taken, but the target address is not one thing. You can return from many different places, right? So what your next address is really depends on where the original call happens. If it happens it could happen at different places, so your return address might be very different, right? And then you have indirect branches, particularly in RISC-V architecture, that's your JAL-OR, that also always taken, so it's an unconditional branch, but the target address could be many, many different addresses. So basically, for example, if you have something like JAL-OR, like X0, X1, some offset, then or I think the offset is here, but anyway, this depends on the value of x1 and the value of offset. If I change the value of x1, the base is different, the target address will be different. Okay, so now that looking at this, let's see if BTB going to be helpful in these systems. Yeah. Yeah, so unconditional one for RISC-V under this terminology is just JAL. Yeah, just JAL. Is JAL, yes. So I mean, technically, JAL-OR is also unconditional, but what I'm saying here is that since I know the address, unconditional, direct unconditional is JAL. Okay? You had the question? Yeah. So that's so the question is, how do we know which one, like what is the difference between the unconditional and indirect? So the difference is because that, remember JAL and JAL-OR, right? So JAL-OR, the target address was based on the register, the base. So both of them are base plus offset, right? But the difference was that the base here and the base here was different. In JAL-OR, the base was the register that you're providing as the source. In JAL, the base was PC, right? So that's why it's always jumping to the same address over and over again. If I see the same instruction, it always go to the same place for JAL. But for JAL-OR, that's not the case. If I change the base, it jumps to somewhere else, right? So that's why it's different. Let's actually look at this, right? So BTB, if I have an RTOS, if I have basically non-control flow instructions, then BTB is helpful because essentially PC will be always PC plus 4, and it's not going to be a match in the BTB. So BTB is not gonna basically negatively impact my non-control flow instructions, right? Then for JAL, basically, since I know that this is always taken and the address is always PC plus offset, BTB will be great because whenever I see a JAL, boom, I go to BTB, get the address, and then go to the next one. Okay? For BEQ, I know the target address is PC plus offset, but whether or not I'm taking the branch depends. So BTB kind of helps, it helps when the branch is taken, but it doesn't help when the branch is not taken, right? And lastly, for things like return call and Jalor, which the target address is also varies a lot, then your BTB is not that helpful, because not only you see the same branch, it might be a hit, but the target address may not be the same. So it's not about the direction, it's also about the target. So for indirect branches like return and Jalor in general, BTB may or may not be helpful, because if your base address is changing, BTB is not going to be helpful. It's actually going to be negatively impacting your performance, because you do a misprediction and you have to flush and all those stuff. So you might actually be better off without a BTB. Okay? So let's see actually how do we improve this. So BTB helps, but to some extent. That's kind of the summary of this slide. Yes? So the question is that for last one, why BTB is not helpful, right? Remember, like a table like this, right? So I have the PC and the target address, right? And I see the branch the first time. So let's say this is Jalor instruction. So I put the Jalor instruction here, and I have the target address, okay? But let's say the Jalor instruction is like something like this, x0, x1, and then the offset, okay? So now let's say I have some bunch of instruction, and somewhere within these instruction, I do something like add x1, x2, and x3 or whatever, right? So I'm changing the value of x1, okay? And now I'm going back to this JAL sometime in future. So it's still the same JAL, it's same PC, it will be a match, but the target address is no longer the same, because x1 is different. So your target address is not the same. So it's not like, oh, if it's a match, it's great. For JAL, it was. For Jalor, it's not. Because your target address keeps changing based on the application that you're running. Okay? Yes? So if you see it before, we predict taken, right? If we didn't take it the last time, yes. So for now, we just BTB is one single thing that is, if it's there, predict taken. Later on, we're going to actually improve. Yeah. Okay. So based on these things, the question is, can we do better? And obviously, the answer to this is we need to predict dynamic, right? So we need to be able to kind of differentiate between different types of branches. We also need to be able to differentiate between the outcome of branches. For example, the question you asked, that maybe this branch was not taken last time. Why are we taking it this time, right? So this is the idea of what we call a branch prediction or dynamic branch prediction, okay? What is the key idea for dynamic branch prediction? Is history, okay? Basically, any sort of branch prediction is based on this very important insight that whatever we did in the past, it's likely that we're going to repeat it. Okay, so that's why we always maintain some level of history. The history could be just the last time, could be the last 6 times, it could be the last 64 times, it could be any sort of combination of the previous history. We try to remember that history and make the decision based on that history, okay? So that would be basically kind of like the majority of the logic in any of branch predictors that you will see is based on this very simple thing, that just the branches tends to repeat their behavior. So for example, think about backward branches. Think about for loops, right? The first time that it goes back, second time is also very likely that it goes back. Again, we're not going to get 100% accuracy, but the majority of time this would be very accurate, right? So that would be the idea of a branch predictor. So how do we track history? We will use memory. Okay, so we basically use registers and memory and log the previous behaviors. Think about branch and code taken and not taken as zeros and ones. Okay, so basically I can store a vector of zeros and ones, where 0, for example, means not taken and 1 means taken. And I store that vector along with my branch. Okay, so basically I can, for example, see that if it's all 1, 1, 1, 1, 1, right, which means that the last, let's say, 8 times it always was taken, then it's very likely that this time will also be taken, right? So we're going to do basically kind of like that. So we're going to store this as zeros and ones, and then we're going to refer to that and make some decisions based on that. Yes. Yeah, I'll show you like basically this would be the architecture. The simplest thing that you can do is a 1-bit history, okay? We usually call this a branch history table or BHT. We're gonna basically reuse the architecture that we had in our BTB. We are adding this additional column, and this is just 1 bit, okay? So remember that I had the tag and I had the target address. Now what I'm also storing is 1 bit in the middle of those two. That is stored either 0 or 1. And 0 means that the last time I saw this branch, it was not taken. And 1 means that last time I saw this branch, it was taken. Okay? So, and this is how I'm going to basically update my logic. I still check the tag with this tag. If the tag is not matched, it means that I haven't seen this branch, so not taken. So there's no other things that I need to do. If I haven't seen it before, predict not taken. But if I have seen it before, then the next step is that I take the history and I end it with this 1. So the idea here is that if the last time this value was 1, which means that we have taken this branch, the value of this and will be 1. So we take the branch. If the last time we saw this branch, this value was 0, so the branch was not taken, this value will be not 0, this value will be 1, the and will be 0, we're not going to take the branch. So last time we didn't take the branch, this time we will also not take the branch, okay? So that would be basically the dynamic behavior, because essentially putting 0 or 1 here will change the outcome of the prediction. If it was 1 and it's a match, we'll take the branch. If it's 0, we will not take the branch, okay? So here's what we're going to do, right? So essentially for all the unconditional branches that are always taken, all I need to do is basically put a 1 here, right? So for any JAL and JALR and all that, I can always put 1 because this branch has to be taken. For conditional branches, okay, I need to do some logic. So I'm going to show you how we make the decision. But for now, since it's only 1 bit, we basically see the actual outcome of the branch during the decode, and I put that number here. Okay, so if this time the branch is taken, I put 1 so that the next time I see this branch is also going to be taken. The next time I see the branch, if it's not taken, then I'll update this and would be 0. Again, this will not be accurate all the times, but assuming that the branch repeats itself all the time, this will be very accurate. Yes?
Exists inside the attitude part of the table.
Yes.
If it does, the history bit.
Yes. If it's 1, if the history is 1 and the tag is a match, then we take the target. If neither of these two is correct, you don't take the target. Index is just making sure which row of this table you're going to, right? So you need to see where do you store that, right? Yeah. Yes, you take the row. So you say, okay, this is the row that I need to look at, and then I take the top tag and compare. Okay? Yes. Okay, so basically your history BHT looks like something like this, that it has 2 states. It's like a state machine. It has the predicted state, predict taken state, and predict not taken state. And then if we are in this state of taken, and if the outcome is indeed taken, we stay in this state, right? So we predict taken, the outcome is indeed taken, you stay in the taken state. If you are in a taken state, but the actual outcome is not taken, this is misprediction, right? So you predict taken, but actually later in the decode stage, you figure out that this was a not taken branch. You have to flush, but you also update your state. You say that, oh, okay, the last time this branch has not been taken, let's actually switch to the not taken stage, okay? And then you stay in the not taken, you continue staying in the not taken as long as you're seeing the same outcome, which is not taken. And then you again switch back to the taken if you see that the outcome is taken. So this could be back and forth between the taken and not taken state. But the idea here is that if the branch tend to do similar things over time multiple times, then this would be a fairly accurate branch predictor. Okay. So for example, if you look at this pattern, let's say I have a pattern of taken, one not taken, and then bunch of takens, okay? And let's see how our branch predictor behaves in this system. So if you actually look at this, our branch predictor, let's say originally we start from the taken branch. So generally where you start is just the initial conditions of your branch predictor. Doesn't matter which one you start, you can make assumptions. We usually give you an assumption of, okay, consider that this is a taken stage. So let's say originally my branch is in the taken stage, okay? So I'm in the taken stage. What I'm going to predict is going to be taken, okay? And then what I will see is also taken, which means that I'm going to, at this point, I'm going to stay in the taken stage. The next branch comes, I will predict taken. I stay taken. And then this continues until I reach to this branch, okay? At this branch, since the previous stage was taken, I'm going to predict taken again, right? Because last thing I saw was taken, I'm going to predict not taken. Oops. I'm going to predict, so this was the last thing I saw, as a result, so I'm going to predict taken. But this means that this is a misprediction. So this is a misprediction, okay? And the important thing is, according to this, if I see a not taken outcome, I'm going to switch, okay? So at this point, for this branch, I'm going to predict not taken. Why? Because the last branch that I saw, which was this one, was not taken. So this will be a misprediction as well. So these two will be two mispredictions. But then I'm going to, since this one, the actual outcome was taken, I'm going to switch to the taken stage. And then the next branch comes, and now I actually predict correctly, because last thing I saw was taken, I'm predicting taken, okay? So as you can see, if I'm kind of continuously do the same thing, this branch is fairly accurate, right? Because if I see taken, I can basically capture the most of this behavior, right? I kind of miss things that are like rarely changing. And as a result of that, there are two misprediction. One, because of the first time I saw it, and second time because I'm quickly changing to the other state. But overall, if I see like out of the 10, I get 8 correct. So 80% accuracy, fairly reasonable. Yes.
For example, this case, like it was TNT until we see again. TNT and
Yes. So essentially, if I have a pattern of taken, not taken, I'll mispredict whole way. So it would be terrible. If I have a branch that is like frequently switching, this will not be a great idea, because you're always like one phase away, behind of the actual behavior of the branch. Yeah. The taken, not taken. Question is how common that is. It's for if then else's could be common, right? For for loops and while loops is the actual given pattern, like the black pattern, is more common, right? So but yeah, for highly, this is what we call a highly dynamic branch, right? Like it's like changing a lot. So yeah, it's not great. Okay, so we actually kind of like You had a question?
I think, but the problem for birds and birds is so big.
Yes, yes. So we are still not fixing the problem of indirect branches. We're not fixing the problem of target address. We're just fixing the problem of direction of the branch at the moment. Yeah. Yeah. So, just a conversation that emerged that this kind of changed too quickly. So if I actually have a branch that is quickly changing, this branch predictor is not that great, right? Because it's also very sensitive to any sort of difference, any sort of change of behavior of the branch history directly impact our decisions. Very sensitive. So how to make it less sensitive? You can actually go with what we call a 2-bit predictor, which essentially what it does is that it doesn't look at just 1 bit, but it looks at the last 2 bits, right? So the idea here is that last 2 bits probably gives you a little bit better kind of history, a little bit longer history, so that you can make a decision, okay? So it's still I'm predicting either taken or not taken. So my outcome is 0 or 1, but my states are now 4 states because I have 0, 0, 0, 1, 1, 0, and 1, 1, okay? So here's what I'm going to do basically. So I'm going to divide this lower part into the taken prediction and this upper part to the not taken prediction, okay? So basically what we are saying is that if the last 2 branches were taken and taken, then obviously you want to predict taken, right? And if the outcome is indeed also taken, you stay in this. This is what we call a strongly taken. It's taken and it's also very strong. Then I have 1, 0. This means that the very last one was taken, but the one before that it wasn't taken. We still predict taken because we give a little bit more value of the last one, but this is called a weak taken. So we kind of like, we are ready to switch to not taken if the next one that we see is also not taken. So we basically switch from 1, 0 to 0, 1 if the outcome is not taken. If the outcome of a strong taken is not taken, we actually switch to the weak one. So still we predict taken in the next time that we see this branch. So it takes 2 not consecutive not takens for us to switch from 1, 1 to 0, 1. Okay? And same story for not taken. If it's 0, 0, it's a strong not taken. If it's 0, 1, it's weak not taken. Okay? So that's kind of like the predictor. This is what we call a 2-bit predictor or a bimodal predictor. The idea is that we are adding some form of a hysteresis, some form of a resistance to quickly changing depending on the outcome of the branch. And we are kind of extending the history to 2-bit such that if the branch is continuously not taken, then that's when we are actually predict not taken. If it's continuously taken, that's when we are actually predict taken. If it's flip-flopping between taken and not taken, we can kind of capture that with the weak not taken taken. Yes? Yes, so there could be also like a corner case where you are in like a strong not taken and then you see a taken, right? And then you see a taken and then there is another one right after which is not taken, and again you're kind of switching. But this is like anything but this will work, right? So if you start here, it will work. If you start here, it will work. If it start here, it will work. But anything like other than this will work. So you much better than what you were. And on average, again, this will not work on all the time, but on average, you are going to perform much better. Okay? So yeah, so you can actually look into the same pattern that we had before. You will see that if I start with weak taken or strong taken, we're actually gonna see that we're gonna continuously predict taken, because at this point we're going to be in the 1, 1 stage. We're gonna stay in the 1, 1. So even if we see a not taken, we're gonna still predict taken. We're gonna go to 1, 0, but then the next one will be also taken. We're gonna go back to 1, 1, 1, 1, and so on. So There will be at some point we go switch to 1, 1 and staying in 1, 1 and only switch to 1, 0. But the difference between this and this previous one was that we are slightly more accurate because we are getting rid of this one extra not taken that we had in the past. So from like 80% in this particular example, we increase the prediction accuracy to 90 to 95. Okay. In fact, actually, a bimodal predictor on average is like 85 to 90% accurate. But of course, the downside is now we need 2 bits history, right? So what used to be 1 bit BHD is now 2 bit BHD, and we need to do this for every entry in your BTB table, right? So slightly more storage overhead. Okay. Any questions here? Cool. All right. So 2 bits bimodal is kind of like the gold standard for branch predictors. So almost all the kind of advanced systems use some form of a bimodal. But of course, there has been tons and tons of research on improving the branch predictors. So the story of branch predictors has been massively worked at, especially in 90s and early 2000, because that was the time that processors performance was like going up, and branches was really kind of holding the systems back in terms of performance. So there was tons of research on branch predictors. There is still research on branch predictors, but the research, I would say, has slowed down because we kind of like, there's not much more to kind of advance. We really like exhaust all the possible options. But this will be basically what you're going to do in your CA number 2. You're going to design your own branch predictor. You can try different ideas to actually improve your branch predictor. So you can start with a simple bimodal and start thinking about how to improve it. Okay. So here's some ideas to give you in order to improve. So you can use what we call a history of history. So usually many of the branch predictors use what they call a global history and a local history. Global history means that all the branches that I've seen recently. Local history means that maybe I can also use PC to kind of differentiate. So instead of having one table for everything, I have smaller tables, okay? So I have multiples. I have multiple of these BHDs, okay, which are indexed based on PC. But then I also have a global history like 0, 1, 0, something, something, 1, 1. So this is basically the, let's say, the last 16 branches. And based on these recent branches, I'm going to pick one of these tables. Okay. So the idea is that if your kind of branches are changed, for example, think about function calls. In one function, your behavior of the branch is different than the other function, right? So what you want to do is that, can I kind of somehow separate the history of this function than the history of this function? This is kind of like somewhat what it gives you. So think about each of these as a one function. And the way that we kind of differentiate these functions from each other is based on the past history. So it's kind of like the past history of branches kind of give you some idea about where you are in your program. And then you can actually look at the tables there. There are a whole bunch of other ways of like, how do you actually combine this? There's another thing called tournament predictors, that you have a bunch of different predictors and do some form of a majority voting. The one that is actually very common and most of you are going to probably implement that is called tagged or TAGE branch predictors. That has basically what it is a glorified version of what I just showed you here. So it's kind of like a tables of bimodal predictors and some form of a mapping technology or techniques to kind of decide this. So there's a whole bunch of this. The ultimate idea in a branch predictor is you want to use your spatial and temporal locality, okay? So your temporal locality is your history. Your spatial locality is your patterns, like, you know, where my PC is and what is the recent sequence of branches. These things will give you spatial locality. And temporal locality is basically the memory that you have in each of these tables. If you use this the right way, then you will have a very accurate predictor. Of course, like many other things, machine learning has been used for branch predictors. There are neural branch predictors where you can basically think about branch prediction as a learning problem. There is a sequence and you want to predict the sequence, right? So you can actually use machine learning or now generative AI to create the sequence for you, right? So think about this as a sequence of zeros and ones. I'm asking what is the next one? Given the sequence, tell me what is the next bit. Is it going to be 0 or is it going to be 1, right? So it can be a generative problem for those of you who are interested in. And there could be hybrid. It could be a combination of a bunch of different things. So for you, this is kind of like, homework for you guys to look at it. You will use it in your CA number 2. Okay? Questions? All right. All right, so one last thing. So what do we do with Jalon? What do we do generally with indirect branches? Okay, as I told you, usually we use a separate indirect predictor. I'm not going to go through the indirect predictor design, but just keep that in mind that usually for indirect branches, using BTB is not a good idea. We usually use a different type of predictor for these things. But for return and call, there is one simple solution, and that is using some form of a FIFO or a stack. There's this thing called return stack buffer or RSB. Basically, return stack buffer, think about it similar to BTB, but it's a separate unit. And all it does is that it basically maintains a stack of return addresses. When there is a call, you push the return address into the stack. Then the next time you're going to return, you pop this address from that stack, and that gives you a very accurate response, right? So to give you the exact target address that you need. So if I maintain a stack for my call and return addresses, whenever I see a call, I push the return address into this stack. Whenever I see that branch, I can basically ask my RSB to give me the address. Okay, so that would be basically the idea of return and call. Whenever I see a return, I pop it from the RSB. How do we actually design this together with the BTB? You can think about the BTB as kind of like, as I said, in the modern processors, your actual branch predictor is a bank of different things. You have your BTB, you have your RSB, you have what we usually call a backing predictor. So you basically consult all of them, and there is usually a logic to decide which one you want to choose. So your branch predictor logic is combination of a bunch of different things at the same time, and then you decide which one to choose based on the opcode or based on some other prediction and so on and so forth. Okay, this backing predictor is, for example, your high-end branch predictor, whatever it is. So like your fancy branch predictor is basically this one. Your RSB is here and your BTB is here. Okay, so that's usually what, if you look at the latest and greatest like Intel processors, this would be the design of their branch predictor. Okay, and sometimes these branch predictors are so complex that they take multiple cycles to decide. So your fetch states is not going to be one cycle, it will be like 4 cycles. Why? Because your branch predictor needs to do all of these decisions and all that. But since your pipelines are very deep, okay, it's very important that your branch predictor becomes accurate. That's why you're willing to pay the penalty of extra cycles to make sure that your branch predictor is accurate. So just keep that in mind as well. Okay. All right. Yeah, that's it for the branches. Any final questions? All right, let's have a quick break. When we come back, we're going to review the content for quiz 1. All right. Review. So for CA1, you can, as I said, upload as many times as you want. Do not zip your files. If you zip your files and upload the zip files, the script cannot compile it, and then you can run into compiler. If you're code does not generate anything, and it basically says that, you know, expected output and nothing is shown, it means that you have a compiler, most likely, okay? If you have a compiler, a few suggestions to you is that make sure that you have, obviously include all your files. Second is that if you're using any special libraries, make sure to include them. And then if none of these things work, you can DM me on CampusFire and I can see the log for the compiler and then I copy that and send it to you so you can actually see it. If the code for some reason does not work on, it does compile and produce results, but the results is different than the results on Gradescope, that's some form of like a nasty bug somewhere in your code. How to debug it, two things that I've seen. One is, it's usually because of initialization. So either your registers are not properly initialized or your memories are not properly initialized. So it's that's usually the kind of the culprit. Or you're not really reading and writing correctly from the memory, like store board, load board, kind of like logic may be wrong. But if none of these things and you still have problems, you can actually use the output of your Gradescope code as a way to debug, right? So you can, instead of printing the A0, A1, you can also print other things and upload your code and see the outcome, right? So you can always like use the Gradescope output as a means to debug because you have unlimited time of doing this. So create some kind of checkpoints in your code, output that will be, the output will be shown on Gradescope. You can see whether or not your code, like what your code is doing. So you can use this kind of like an indirect way of debugging on the Gradescope. But most people, I don't see any problem. So it seems that at least this year's test working fairly, you know, consistently on local machines. And the reason that it's different is because it's different compilers versions. So that's the reason. Okay, if you have further questions about the CA, come to the office hours today after the class. Also, there are office hours tomorrow from 12 all the way to 6. Go to any of them, ask your questions there. Okay, homework and samples, check out previous samples, quizzes, and homeworks. If you go to the website, if you look at the bottom of the schedule page, it says resources. It has actually links to all the previous years' homeworks and quizzes. You can go there. The solutions should be there as well. You can also, as I said, look at the previous year's offering of the class, and again, you know, find the files there as well. Generally, make sure that you have studied homework 1 and homework 2 of this year's, plus the worksheets that we gave you. Make sure that you study those. Plan to attend the discussion sessions tomorrow. The TAs and LAs are both there, and they're gonna basically go through the solution of homework 2, as well as they have another worksheet that are kind of like some variants of homework 2. Both of them very useful, so try to attend and ask questions there. And then you can also ask questions about other stuff that you have tomorrow, okay? Quiz 1 will be 90 minutes, pen and paper. You are allowed to bring in 3 sheets of paper. You can handwrite it or print it or do whatever you want with it. There's no problem. And it could be front and back. You can write it with like 0.00 font size, or you can make it big, whatever you want to do, that's okay. You don't need to kind of print. So for questions that needs to, for example, change the data path and control flow, we're going to give you the data path and control flow so you can annotate that if needed. But for your own kind of like knowledge, if you want to see and have a mental picture of the control data path, you can put it in your cheat sheet, obviously, as well. Any part of the lecture, if you think it's necessary for you to kind of remember, put it in your cheat sheets. You're not going to be allowed to use calculators or cell phones or tablets or phones. There might be a slight conversion from decimal to binary. So make sure that you can convert a decimal number to a binary number and a binary number to a hex number. It's not going to be like a long list of binary to hex, but it will be maybe one. So maybe make sure that you have. Yes. Where you can find worksheets. On campus fire, there's actually pin. Yeah. Let me repeat that question. So the question was where we can find the worksheet, and it's on campus fire. It's a pin. It's a folder. Yeah. Yes. No. So the question is if, for example, if we give you the design of a single cycle and say that, oh, add instruction such and such to this, we will print the thing inside the question. So you can only kind of draw things on top of it. Yeah. Make sure for all the questions, very detailed, show your work. Even if the question doesn't, something that is always like really kind of cause inconvenience for the students and for the grading is that we ask you what is the value and you've just put the value, and then your value is incorrect, you don't get any points, and then you say that, oh, why don't I get any points? Show your work, even if the question asks you to give you a final number. Show your work, so then we can give you partial grades, even if you're kind of like you miss one final thing. Okay. If, for example, the math, since you don't have a calculator, for some reason the math is asking you to multiply two very large numbers and you don't feel like multiplying the two numbers, write the full equation, right? Say that, okay, the final value would be multiplication of this and this, we will accept that. So we're not like looking for a final number. As long as you show your work and the formulation, that's okay. There's not going to be like a big multiplication, but just in case, okay? And then in terms of the topics, everything up to what we just said today. So make sure that you watch, you guys that are already in class, I think you're good to go, but people are watching, hopefully you're watching this lecture or maybe too late. Yeah. Yes, 3 sheets. Each sheet has 2 pages, so 6 pages total. Whatever you want, you can put it on it. I don't care. Yeah, and don't please bring like an A4, right? So not, yeah. Say it again. Oh, yeah. So the things that we're gonna give you, there will be a last page of your quiz that I have 2 tables. I'm gonna actually share the exact same page on CampusWire, so you're gonna see exactly what we're gonna give you. But I think I actually have it somewhere here as well. So I'm gonna give you this. So this will be on your quiz. And then I'm also gonna give you this. So these 2 will be in the last page of your quiz. Whether or not relevant, separate story, but this will be given. You don't need to bring this. Yes. What do I suggest for putting on cheat sheet? I honestly don't know. So whatever you feel comfortable, like having maybe like a picture of your pets, or you can put whatever you want to in the cheat sheet. Technically, you don't need anything. Whatever you want. Yeah. Pseudo instructions won't be given. Yes. Yeah. If we put the pseudo instructions, we'll give you the instruction as well. Yeah. Maybe I'll put the pseudo instruction table on the quiz as well, so that you feel happy. Good. Don't put it on the cheat. Yeah. Okay. If you are a CAE student, you should make an appointment with the CAE center. The normal exam time is 90 minutes. For those of you who need more time, obviously you have usually like a multiplication factor, do that, and then that will be the time for your quiz. What we're going to do is that I'm going to probably upload the quiz on their system, and you usually print it out. But if not, I might actually also Sorry about that. I might actually also give you, yeah, that would be probably what I do. I'll make sure that it's there so it's printed. Okay? Any other questions about logistics? It will be here in person and all that. Any other questions, accommodation needed? Yes. Uh-huh. So the Wednesday discussions would be based for the quiz, right? So I mean, if you need help with the quiz, go to that. The Friday ones is after the quiz. So whatever we say that is important is not relevant anymore, right? So your quiz is on Thursday. If you can't make it, we can try to record, but usually what I've seen is that since it's a Q&A, it's really not much. It's not like we are like presenting anything, right? So it's more of like discussion of the solution. So the solution obviously will be uploaded. The worksheet is uploaded. So yeah. Yeah, so today is my office hours. Come to my office hours if you have questions for CAs or the homework. And as I said, tomorrow, 12 to 2, 2, 4, 4 to 6, go to one of them. That will be TAs and LAs will be available. And another thing that I realized is that the discussion session attendance causing confusion for people and say that, oh, I came to that one, like I didn't get points for this one and so on. So I'm going to actually get rid of the bonus thing. I'm going to give bonus to everyone. So everyone will get 1% bonus. Just go to the discussions if you want to. So it's not no longer required thing. So if you want to go to the discussion sessions, go. If you don't want to go to the discussion session or the schedule doesn't work, don't go. And then we don't have discussion session this Thursday and Friday. Okay. And again, everybody will get 1% bonus. Okay. Question you have? Question is, do we need to know anything beyond the base instruction set, like in multiplication and stuff like that? No, you obviously. So anything that we covered in the class, that's the only thing. So these tables that I show you, that basically what you need. Any other, of course, we might, for example, ask you to like create a random instruction and say that, oh, add the support for this kind of random instruction, like the ones that we put in the homework. Those type of questions we might see. Yes. You can't use the multiplication either, right? So even in homework 1, we said that you're not allowed to use like a remainder or multiplication and stuff like that. I mean, I think the worksheet we were giving you kind of different options, but I'll double check that and then clarify it if we used it. Yes. Okay, so let's review less of like 20 minutes remaining and all. Let's actually review a little bit. So that would be also helpful for you guys for the quiz. So we started with the idea of the ISA, and we said that the first step in designing the mark architecture is coming up with the ISA. We particularly focused on RISC-V ISA, and we said that RISC-V is actually a modular design ISA. It starts with what we call a base ISA, and you add a bunch of other things like the M series and F series and the privilege series and so on and so forth, vector series. The ones that we particularly focused on was these sequence of instructions. We kind of like go through the logic behind them, the types that they have. Some of them were R-type, I-types, what is the difference, and so on and so forth. The important thing about ISA is that you want your ISA to be minimal, but you also don't want to be so minimal that you need to break down one operation into multiple instructions. So it says kind of like there is a sweet spot for your ISA design. Now you want to reduce the number of instructions, because remember in the iron law, if IC was smaller, you get faster CPU time, right? You get better and better performance. So you want to add as much as instructions as possible in the ISA. But on the other hand, if you have too many instructions, then the size of the instruction grows, the pipeline and delays grows. So you cannot like also have a significantly large ISA. So you need to find a balance between the size of the ISA based on the design. So people on the RISC-V kind of foundation think about this is the right kind of, this is the sweet spot, just FYI. Make sure that you kind of understand the difference between these instructions, their operations. Like, some of them were signed, some of them were unsigned. Try to kind of like make sure that you kind of feel good about this table and understand each one of them. Okay. Then we also talked about machine code. And then in the machine code, we had another table that basically breaks down the instructions into different parts. Opcode, RD, RS1, RS2. Some instructions has some of these components, some other instructions don't have these components. Generally, in RISC-V, we have 6 type of instructions, right? And each of these instructions that we know of is part of this. Make sure that you know which one is where, like where is func3, what is the role of func3, what is opcode, what is immediate, and so on and so forth. So generally understand, like if you're given an instruction, you can actually kind of say that, oh, RS1 is this and RS2 is that, and so on and so forth, and you can kind of distinguish between them, okay? And then, of course, for this, I'm assuming you now kind of so-called experts, given that you have done CA1, which is actually you have to go and really implement this, every single part of it. So hopefully if you've done your CA1, you should be fairly comfortable with this. So, and then homework 1 for like a translation between binary and so on. After that, we talked about the microarchitecture. We said that essentially we are implementing a one Neumann machine, which we take the ISA, we generate the binary, we put that binary into an instruction memory of the system, and then we have a PC that kind of like goes through that instruction memory and fetch one instruction at a time and execute that instruction. That was kind of the format that we are going after, right? And the design that we went after was a design of a data path plus a controller plus a memory, right? So the controller was the one that's kind of orchestrates the movement of data in the data path. Data path was combinational and registers that we put in order to do the operations. The operations was like things like instruction fetching, register file reading, multiplexing, immediate generation, ALU operation, all that, right? So that was like our data path. And obviously we spent a lot of time talking about this. This was like a simple single cycle instruction microarchitecture that can only support 10 instructions that we listed in the lecture. So this does not support all the instructions. And then, for example, in the homeworks, we ask you to add support for another instruction in the system. Another thing that we ask you to do is being able to kind of measure the delays, the propagation delays for different components in the system. And kind of, if you remember, I gave you the analogy of water, and the water is kind of like, moving toward different directions, and you have kind of these gates or these barriers. Try to make sure that you understand how the logic propagates, how the delays can be computed. These are important topics in general. And the things I'm saying is that generally these are important things for you to know from this course. Whether or not you're going to be part of the quiz is a separate story. But just generally make sure that you understand these things going to be later also useful in this course. Okay. And again, I'm assuming that you're fairly comfortable with this design because this is what you have implemented in the CA1. You also should be fairly comfortable with adding new features to this. For example, you implement LUI or JAL and ORI and stuff like that, which wasn't initially implemented here. So I'm hoping that you can and comfortable with like adding more things to this. Okay. So as I said, what are the components? Sometimes you need to add a controller, sometimes a control signal, sometimes you need to add a new components in the data path, sometimes you need new wiring, combination of these things. Yes, sir. How long that delay would be? What do you mean? So you mean like the numbers? I mean, I'm assuming that in order to compute the longest path, you need to have the numbers. You need to identify the components anyway, right? And then the mapping of the components to the numbers is just looking at the table, right? I mean, so the question was like, in order to compute the delays, do we need to detect the critical path, or do we also need to come up with the numbers? I'm saying that generally these are one-to-one mapping anyway. Yeah, so for example, we had examples for like data flow of something like a load board. And as you can see, load board, for example, not all the components are used for all the instructions. And as I said, for a clock cycle, for single cycle, the important thing is the maximum delay. The worst case delay is the one that is basically determines the cycle time. We also then talked about iron law of the processor. We said that essentially what we want to do and what we care about is reducing the CPU time. And we also talked about benchmarking and throughput and latency and the difference between them. But ultimately, you want to reduce instruction count, cycle per instruction, and cycle time. We talked about each one and how you reduce them for a single cycle. We also talked about it. Then we start talking about pipelining. Essentially, the idea of the pipelining is that if you have a large combinational path, we can break it down by adding these pipeline registers. The good thing about pipeline registers is that if this critical path was t second, if I add pipeline registers and divide it by half, now my clock cycles is 1 over like half of that, right? And my throughput as a result can increase by a factor of 2 if I have the overlap. If I don't have the overlap, of course, my throughput stays the same. I'm not going to get any benefit. But if I can put pipeline registers, there are two good things that are happening. One is that I can use the overlapping, and second is that I can reduce the cycle time. So two things results in faster communication, faster computation. And then you can continue doing that. The design that we went after was a 5-stage pipeline. As I said, in modern processors, 5-stage might be more. So 10, 15, 20 stages of the pipeline is fairly normal in many systems. The ones that we go after was this, but just keep in mind that this is not just one example. There could be examples of multiple stages of the pipeline. So if you see, for example, that there is a design that have multiple stages, more than 5, don't be confused. This could be just like someone decides to kind of break this down further, right? And as I said, modern processors are actually way, way more than this, okay? We also then talked about this design, this particular pipeline design for that 10 instructions that we had. And the big thing here was now you're overlapping. So now there are multiple instructions in this pipeline. So each stage has a different instruction. So this is stage versus this is stage versus this is stage versus this is situation. This is stage. We talked about the fact that now values and wires have different values depending on the instruction. So it's not like single cycle where the same value was the same thing throughout. For example, your control signal in the decode stage is very different than the control signal in the memory stage, very different than the control signal in the write back stage. So make sure that you understand these timings, these connections, and so on and so forth. Okay? That was the kind of the story of the basic design of the pipeline. Then we also talked about hazards. We introduced 2 important types of hazards, the data hazard and control flow hazard. Data hazard, we talked about 4 different types of hazard. We said that essentially all the others are not important in order processors. The only one that we should care about is raw, which is read after write data hazard. Examples of that was this. We said that if you don't do anything for this, you have to stall the processor for 2 cycles. But then there are 2 options. And by the way, I'm assuming that you're now also familiar with the half cycle idea, that we can write things in the half cycle and then read it in the next half cycle. That's why I can basically, this last instruction can be going successfully in the pipeline, because I read X5 in the second half cycle of the decode, but I write it in the first half cycle of the decode on the same register file. Yes, sir. So the question is, out of these 5-stage pipeline, which one has the half cycle? Half cycle is when you're writing to the register file. Okay, so writing to the register file has this notion of half cycling here. Any registers that you have in the system has the half cycle component. Memory, no. Memory doesn't have half cycle. So memory takes the full cycle to read. So you cannot read and write the same address in the same cycle. and you can do it anyway. So it's not like, it's any given point, there's only one instruction in the memory. The reason that you have it in the register is that you have the RD and RS in the same cycle. These are coming from two different instructions. Okay, so how do we fix the raw data hazards? We talked about two solutions. One was stalling. We said that 2-cycle stall is one option. It's not great. It reduced the performance, but it's simple. And then we introduced the idea of forwarding. For stall cycling, as I said, 2 cycles. You can think about the compiler can actually do this for you if you want to. So what the compiler would do is that inserts what we call a no-op or bubble in between the instructions that have dependencies. But usually what we do is that we do it in real time dynamically inside the hardware. The way that we do it is that we basically kind of see that there is a hazard. We have this thing called hazard detection unit. That what it does, it basically frees the processor in the fetch and decode stage, and then inserts what would have been the normal instruction going through the pipeline and replace it with the no-op or bubble instruction, which was basically just a simple zeros that we kind of let to move through our pipeline. How do we implement this? As I said, we basically put a mux in a way of the controller. When we decide that this indeed needs to be bubbled, what we do is that we have this hazard detection unit, which basically check the condition. And then what it does is basically saying that, oh, okay, whatever control signal was, don't do it, send 0 from this point on, right? And then what another thing that this hazard detection unit does is that it basically frees the fetch and decode stage. It stops fetch and decode from advancing in the pipeline. So basically disable the write enable for the registers of PC and instruction fetch / instruction decode pipeline. So two things happened. We feed the bubbles into the pipeline and we stop the processor from moving forward. Okay? Yeah, so these are the two things. And then we also introduced the notion of forwarding. We said that essentially the way that we can do things is, since I have the correct value of X5 here, so the X5 that I have here is the updated X5. So why don't I use this pipeline register to forward whatever junk value that we are reading here and replacing it with the correct value, right? And we can do it from both this register and from this register. So the pipelining can happen from memory to execution and could happen from the write back to the execution. Both of them are possible. How do we implement this? We basically introduce this forwarding unit and this multiplexers, and then forwarding can happen for RS1 or RS2 or both of them. So they are done independently. So we can forward from any of the previous two instructions to either RS1 or RS2 or both of them. So either I forward from here or I forward from here, and then that would be basically the values that I'm sending to the ALU. So I'm replacing the value of what I'm reading here. I'm replacing this with the values that I'm getting here. So I no longer want this. I either want this or want this. Which is safe. So I either forward from here, right? Actually, here is nice, easier too. So I either from this register here, I forward from this register here. This is the write back stage, right? So this register is similar to this register, right? Okay. Yeah, as I said, forward from either mem or write back. You can forward to RS1 or RS2 or both. And this is the condition for forwarding. Essentially, what you need to check is that whether the destination register either in the memory stage or in the write back stage is the same as either RS1 or RS2 of instruction that is currently in the execution stage. And as I said, the second thing that you need to check is whether or not this instruction that is currently in the execution stage is indeed going to write to the memory, right? So that's what you want to check. If you want to forward from the memory. If you want to forward from the write back, same story. You want to see that this instruction is indeed updating the register. That's why I need to forward it. And then same condition here. And as I said, you don't need to forward if you have X0. So just keep in mind that X0 does not create any sort of fraud in the hashes. Okay? So what is the good thing about forwarding is that if forwarding is done right, you can basically prevent the stalling altogether, except for one case, which is the load instruction. That was what we call load use data hazard. The reason for this was the data is not available at this point at the beginning, but it's only available here. So if I immediately want to use the value that I read from the memory, I cannot forward it. I need to stall one cycle and then forward it. Okay? So basically it would be a no op in between. I forward from here to here and I move forward. Okay? This is the condition. So the condition is slightly different. The reason that I need this is because I want to be able to stall the processor first and then forward. So this is the condition for checking the stall. This is not a condition for forwarding. This is a condition for detecting the stall. Okay? And then combining these two together, you have the data hazard and you have the forwarding in it, and you have this bubbles inserted here. Okay? So this is when you want to stall the processor when you have when you only have load use. So everything else is fixed with forwarding. You only have load use, and that will be the bubble that you want to insert one cycle from the decode to execution. Yes. You stall after every load if there is dependency, not after every load altogether. Yes. If the condition is met. So essentially, if it has to be a load, but it also has to be the RD of the execution has to be happen to be one of the two, or either both of them. Okay. So the source registers of the next instruction has to happen to be the destination register of the load instruction. If forward forward right after execution, so wait to look what's in memory. Yes, yes. So you want the data from the memory, right? So you don't have it at the beginning of the memory. You only have it at the big end of. So you kind of need a situation like this, that you need a no op in between, so that then you can. So then that no op comes from the stall. And the no op lasts one push everything. Yeah. So you technically, what is really happening here is that you are pushing bubbles here. So this is still your sub instruction, right? And here is your zeros. So zeros kind of goes through. Right? And then here you let the sub goes, and sub now is here, and then you move forward. Okay? One stall eventually cause 3 bubbles, right? So one stall doesn't create 3 bubbles. One stall creates, so the bubble is created during the decode, but the bubble won't be destroyed, right? It has to go through the memory and write back. So yeah, cycle by cycle, you just push it from the decode to the execution. First cycle will be in execution. Next cycle will be in memory. The third cycle will be in write. Yes. Yeah. Basically, clarify. Look for results and correct. When you have load word, your results are available end of the memory. Right. Correct. You forward from write back to the execution. Store word, you're not waiting for any results to be written to the registers, right? You're writing to the memory. So you're not, you don't wait for anything. Yeah. Mm-hmm. So the question is that if I have a situation like this, that I have a store to one address and happens to load same address, right, into some registers, right? What is the situation here? So this is actually, later on, you're going to see that this is a problem. But right now it's not going to be a problem. So why it's not a problem? So essentially what will happen is that I have a store and I have a load, right? So this would be fetch, decode, execute, memory, write back, right? So this would be fetch, decode, right? Execute, memory, write back. So the value of the memory that we want to load will be updated at the end of this cycle. Yes? Great. So here, do I need that value here? No. Do I need to read that value here? Also no. Do I need the value here? No, because here I need only the address and I can compute the address. I only need that value here. And as you can see, it's conveniently actually one cycle after. So we're good to go. So no problem, because as long as it's available at the end of this cycle, which it is, next cycle I'm good to go to read it, right? So if my memory is one cycle only, it's okay. If somehow some complication that like store takes like 3 cycles, then you're gonna have a problem because now the value will not be ready. Later on, you can also introduce what we call out of order execution, that you happen to like do this before this. There's going to be a lot of problem there. So we're going to have what we call memory ambiguity. And now we need to do what we call memory disambiguation, which is you need to forward things even from the memory side as well. We're going to talk about that. No forwarding is required because things are just happens to happen at the right time. Yeah. Uh-huh. At this point, we don't need to, so we're not worried about branch prediction or branch or control flow hazards yet. Here, we are not doing anything about, so this is just anything besides branches. This is only for load use, right? For load use, even if you resolve things at the decode stage, you still need to stall. So it's a raw data hazard. For decode, that was a control flow hazard, separate story. So for load use, there is no solution. You only need to stall, always need to stall once. Okay. Hazard detection unit, stall, make sure that you understand these conditions, this graph. Conditions here. Yeah. Good? Yeah. This one? Uh-huh. Yeah, you don't need to forward, right? Because you want that data here, you update the memory here, right? Why do you want to forward? Yeah. So the reason that the store on word doesn't need the forwarding because these things happen during the memory stage, not during the execution. If I needed the value of the memory during the execution stage, which is the case for load use, then you have to stall. For load word, in the execution stage, remember you were computing the address. And for that, you need RS1 plus the offset. You don't care about what is inside the memory yet, right? So, okay, I want to finish this before I go. So let me actually just very quickly go over this and I let you guys go. So for the branches, we will have the problem of control flow hazards. The problem with the control flow hazard is that if I want to keep the pipeline going, at some point I need to jump over things and I don't know what to do. So how do we fix it? Again, we go back to either stalling or speculation. So forwarding is not going to help in case of control flow. But the other trick that we are using is speculation. We guess, right? So we say that, okay, either this branch is going to be taken or not taken, or we can make, dynamically decide. But eventually we kind of make a guess and we're going to jump. So first question is, how long should we stall? For this design, we said that we need to stall for 3 cycles because we know the outcome of the branch at this point, okay? So this is basically the number of cycles we need to stall. But we said that essentially what we can do is that we can also predict. For example, we can predict not taken and don't stall. We always predict not taken. If we made a mistake, we can always go back, flush things, and redo things, right? So that gives us a lot of performance benefits because for majority of instructions, I might be actually right. If my prediction is correct, I don't need to stall. And then we also talked about how do we flush, right? So the flushing is basically saying that if I read these instructions, I need to replace them with bubbles, right? So essentially the way that we implement this, remember that we had this guy here. Now we are introducing additional muxes to flush more things, right? So we need to now flush execution, we need to flush memory, we need to flush decode, right? So we need to flush three things. So that's why I'm adding these things to the system as well. So essentially, I'm augmenting my hazard detection unit such that it also predicts and find mispredictions. So you can also understand that there was a misprediction and we flush things in the pipeline as well. So yeah, pay attention to this. And again, flushing means that I need to also flush. Sometimes I need to flush other things as well. Okay. So this is what we call miss penalty, right? So when we are flushing, it means that I'm replacing 3 useful instructions with 3 no-ops. In other words, I'm wasting 3 cycles of my time that I could have used for useful things. This is the miss penalty of a branch predictor. In this case, the miss penalty is 3 cycles if you resolve things in the memory. I can give you another design that has 2 cycles. If it's a deeper pipeline, it might be 10 cycles. There are different designs, different miss penalties. Okay. So for this particular design, how we can predict sooner, we can actually move things to the decode stage. The way that we actually do this was introducing these comparator here and this shift and add here. So now at this point, I know the PC plus offset. I also know that whether my branch will be equal. And I also know that this indeed is a branch instruction. So in this case, my miss penalty is only 1 cycle. But there was an additional problem that we need to fix. And that was that, there could be also raw data hazards in the decode stage. So if I want to check the branch equalness of, let's say, X3 and X4, and immediately before that I was writing to X3, I cannot do that anymore because remember that the forwarding logic was only available during the execution stage. So what do? I need to stall my processor, or I need to change the processor pipeline such that I can forward during the decode stage. Okay, so as I said, both of them are possible solutions. In some cases, you can forward things to the decode stage. If you can forward things to the decode stage, you'll go back to what you had before, no stalling required. If you don't have the forwarding to the decode stage, then you need to stall the processor however necessary until the previous instruction reaches to the write back. Okay, so until this instruction reaches to the write back, you need to stall the processor, right? And I think your homework is actually like an example like this, so you can actually see it there. Okay. All right. Yes. And as I said, which one is being used? That depends on the design of the processor. Some designs support forwarding to the decode. Some design doesn't support forwarding to decode. So just keep that in mind. Okay. I guess that's it. Any final questions? All right, guys. Good luck. See you on Thursday.
Thank you, Professor.